So it's a great pleasure to have the second talk of the morning session given by Serge Rosenblum, Weizmann Institute, second lecture on quantum error correction.
Thank you, Ganpathy, and welcome back, everyone. Today is the second lecture of the quantum error correction series. My apologies, I'm going to leave my phone on during this talk just in case. Well, I want to, first I should start by giving a small correction to yesterday's talk. If you spent doing homework and it just didn't work out, it's because I spread fake information. There should be a minus in front of the Y. Again, a result of this non-hermeticity. I's are important. Yes, yes. I erased this I equals +1 thing. Good. So let's start with a brief recap of yesterday's lecture. We discussed error channels, what it means to experience decoherence, and we also started discussing small quantum codes. At the end, we got to the 3-qubit repetition code, which is defined by this 2-dimensional subspace 0, 0, 0, 1, 1, 1. We call this the logical 0. This is the logical 1. So it encodes 1 bit worth of information in 3 physical qubits. And we saw that for bit flips, at least, if you apply a bit flip to the first, second, or third qubit, well, the code space will then go to orthogonal subspaces. And therefore, you can identify in which subspace you are and correct the error. What we're going to do today is we're going to generalize this to full quantum error correction codes, where we can correct both bit flip and phase flip errors. And then we're going to formalize this whole business, which was a bit hand-wavy, and we're going to introduce the stabilizer formalism, which is a very convenient tool for working with quantum error correction. Almost every major code that you can think of can be expressed as a stabilizer code. And if we get to it, we will start talking about the surface code as well. So let's start with talking about phase flip error correction. We already hinted yesterday that in order to correct phase flips, we're going to need, in order to correct bit flips and phase flips, we're going to need some entanglement in our code space so that we can then identify the switch of a plus sign to a minus sign. You need a few terms in order for this minus sign to have meaning. But before we get to that, let's talk about the phase flip channel only, so no bit flips. And this is quite trivial. A phase flip, if you rotate your head by 90 degrees on the Bloch sphere, it becomes a bit flip. Here's our Bloch sphere. And well, we know that the X operator flips you from 0 to 1 and from 1 to 0. Likewise, the Z operator will flip you from the plus state, which I define as 0 plus 1. It will flip you to the minus state, which is 0 minus 1. And so the Z just acts as a bit flip in this dual basis, or sometimes called the Hadamard basis, which is a basis of X eigenstates. So Z on plus is minus, and Z on minus is plus. It will not surprise you then that the error correcting code for correcting only bit flips is a repetition code with code space plus L plus plus plus, and minus L is minus minus minus. So these are my logical plus and my logical minus, and I can now detect any error by looking if if these two are the same, and then if these two are the same, exactly the same story as in the bit flip case. Questions before we move on? Okay, so let's move on to general single qubit errors. We're going to use a concept called concatenation. It's a way to take a small code and build larger code families out of it. So this is our first step into constructing larger codes. What we're going to do is we're going to start with a bit flip code. We encode 0 as 0, 0, 0, 1 is 1, 1, 1. This will give us protection against bit flip errors. Now we're going to take each one of those and encode them in another level of error correction, which is the phase flip code, this one. So my new code is going to be plus L, plus, 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 but instead of plus, 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 I'm going to use 0, 0, 0, plus 1, 1, 1. You see, this is the plus state, but it now has an internal bit flip encoding. A lot of writing. As you're going to see, the stabilizer codes are going to come in very handy. Just avoid writing just such long states. The minus state is exactly the same, but you have minus signs here. If you have a bit flip error on any of these 9 qubits, you can detect it by and correct it by observing a flip in the parity within each 3-qubit block. If you have a phase flip error, you can detect and correct it by looking if this phase is equal to this phase or whether a phase flip has occurred. We can correct both bit flips and phase flips. And you can check for yourselves that if we have a Y error, which is a bit flip and a phase flip, then yes, we're going to talk a lot about how exactly we measure. I was trying to kind of leave this out for now. Now, I have a question. If you have a Z error, say on qubit 1, we have Z, I, etc., and we apply it to the logical plus state. What am I going to get? This is my first qubit, and I apply a bit flip, so it takes this plus sign, it turns it into a minus sign. Yes?
So the only errors you consider is an error multiplied by alpha.
Any error that you can write as a superposition of single qubit errors will be correctable by this thing. So, for example, an error such as x5 plus epsilon z5, that's correctable. However, if you have errors such as x6 plus z7 plus y9, this is a multi-qubit error. Our code is not equipped to deal with those in general. Okay? But it doesn't matter if it's a superposition or not. What's important is that you stay confined with single qubit errors. This is qubit 1, this is qubit 2, this is qubit 3. This is 4, 5, 6, 7, 8, 9. Okay, I've taken a block of 3 qubits and I've concatenated it with another block of 3. So I get 9 qubits. And you can convince yourself that whatever error, whatever poly error I apply, I will be able to detect it. I will go to an orthogonal subspace that has 0 overlap with these, and they have 0 overlap with each other. Well, in fact, it's not entirely true. So I was starting to say if you have a Z error on qubit number 1, this is again 1, 2, 3, just a superposition. So it flips the sign from plus to minus. But what happens if I have a Z error on qubit number 3? The same. I get the same minus sign right here. And so we see that these 2 error spaces of Z1, Z3, and also Z2, they are the same error space. Do we care? No, we don't care. And why is that? Because although I don't know if an error happened on qubit number 1, I might have thought that it was maybe qubit number 3 that flipped. If I correct it wrongly by applying a phase flip to qubit number 3 instead of qubit number 1, well, then I correct it to plus. So the correction is the same, or the correction gives the same result, even if you have a mistake and you choose the wrong qubit to flip. So this is okay. This is called degeneracy. This is a degenerate code. It packs more information into fewer error spaces. We'll see that most interesting codes with good properties are of this kind. They have a very large degeneracy. You don't need all these error spaces to be orthogonal. Excuse me? As we saw yesterday, we can work with 5 qubits. By the way, the 5-qubit is a non-degenerate code. It's not a requirement. This was just the first code. It's very intuitive. It's the first code that Shor came up with. It's not efficient or particularly good. But in principle, degeneracy can be used to make things more efficient.
Can you again, suppose you find that there is a final step.
Yes.
What
So if you wanted to annoy me and you apply a Z error to qubit number 1, I get a minus. But I don't know that you applied Z1. I thought someone else applied to Z3. So I'm going to flip Z3 back. In total, what has been applied is Z1, Z3. Z1, Z3 is the identity operation on the code space. It's a trivial operation. Same for Z2, Z1, etc. Or Z7, Z8. Questions from the audience before we move on? We're going to see more examples of this. Excuse me? Yes, Z. If we want to detect bit flips and phase flips, we can do with fewer qubits. And I'm going to use this from now on because it will take me less space on the blackboard. So for detecting, 4 are enough. Remember, a 2-qubit code was enough to detect a bit flip error. A 2-qubit code is enough to detect a phase flip error. And so we're going to need 4 qubits, a concatenation of 2-qubit codes for detecting general errors, general single qubit errors. This is the 4-qubit code. Prabha used this code in her talk. It's very well suited for different purposes. I'm omitting the tedious Brian Ketz, so forgive me for the sloppy notation. There's a thing called a generalized Shor code. You can stick as many 0s and 1s as you want at the price of more qubits, or you can have fewer. It will still behave the same. The principles are the same. Okay? If you add more and more 0s and more 1s, you get better and better protection against errors. Okay, what is the distance of this code? How many bit flips do I need to apply to go from, oh, I'm sorry. Maybe we should rewrite this. I want to rewrite this in the 0, 1 basis. So I add these two to get 0, and I subtract them to get 1. I'm getting even more compact. This was an idea by Victor Albert, I think. Write it nicely in a square. If you got a bit lost, accept this now as our new code. This is the logical 0, the logical 1. And now my question is, how many bit flips do you need to apply to go from the logical 0 to the logical 1? Excuse me? Yes. Oh, this is just 0 for qubit number 1, 0 for qubit number 2, 0 for qubit number 3, 0 for qubit number 4.
the same?
Yeah. It's just more compact, a more compact representation. It doesn't, from now on, it doesn't matter.
Once you start with the errors,
I will write the errors in this way as well. So this is going to be an error, okay, on this qubit. I'm not going to keep track of numbers. I'm going to use this over and over again, so it's a good idea to get used to it. So what is the distance? How many bit flips do you need to apply to these states to get from here to here? 2. So in the Z basis, this is, these are the words in the Z basis. It's clear that the distance is, let's call it dx. And the homework is go to the dual basis. Express the, now go to, write down the logical plus, the logical minus, and write them as superpositions of pluses and minuses, not of zeros and ones. So I want you to rewrite this only with pluses and minuses. And I want you to show that the Z is also equal to 2. Remember, Z on a plus and minus act as a bit flip, right? They change plus to minus and minus to plus. And I want you to ask how many Z operations do I need to apply to mistake plus for minus. Okay? So we see that we have protection both against bit flips and phase flips. What you should do is well, here's the logical plus. You can rewrite plus 0 as plus, plus, minus. And you can rewrite 1 as plus, minus, minus. I hope I didn't get this wrong. So, okay, and then you multiply all the terms. You cancel those that cancel each other, and you'll see what you get. This is an important exercise. Very often when we want to see bit flip correction and phase flip correction, it's very easy to look at a code in the Z basis and then go to the dual basis, the X basis, and inspect its properties there. The code space is span of logical 0 and logical 1. Any superposition of these is a legitimate code word. Good. I want to just briefly mention that concatenation, as I said, can be used to create larger and larger codes. Specifically, here we concatenated a bit flip with a phase flip code, but you can concatenate the same code over and over again. So you take a bare qubit, a physical qubit, and you encode it in, at the first coding level in 3 qubits. So that's the first level. But this is not good enough. You want to protect each one of these. So you can now have a tree like this and go on and on and on. You can have L layers of protection. And so you'll require more and more errors on these qubits in order to create an error in here. And then you go, these were the first codes that were considered, the first code families. You go from an NKD code. By concatenation, you can go to n to the power L. Okay, the number of encoded qubits stays the same. You just protect it more and more. And so the distance becomes d to the L. And now you need d errors for each of these d qubits to create a logical error. You can inspect this and convince yourself that this is the case. Okay, we are done with these small codes, and now we'll talk about stabilizers. Maybe this is a good moment for me to drink and you to ask a question or two. Yes?
When you have a a sign error, plus changes to minus. And as you argued, I don't care whether that was due to a qubit 1 or qubit 3. In principle, if I'm stupid, I could have said that actually it was an error of e to the I pi over 2 of qubit 1 and e to the I pi over 2 of qubit 2. So I could have assigned it, the minus could be assigned to two errors of some different phase factor of qubit 1 and qubit 2. So I'm asking the question from the other point. If you tell me that there were errors in sign of qubit 1, 2, and 5, how do I determine whether I cannot collect all of them and pretend that this is only an error in one qubit? Is there a theorem to tell me when I can correct and when I cannot correct?
We'll get to these general statements of when you can correct and when not. I'll just say that sometimes that in this code you can correct actually more than one error. Okay, you can correct an error that has a phase flip here, but at the same time a bit flip here. So there are 2 qubit or 3 qubit errors that you can correct. We'll get to general statements later. Okay, questions from the students? Yes.
Yeah, so this notion of distance, is it like invariant on the under the basis transformation, or this will depend from basis to basis, which basis I am choosing?
Does it depend on the basis? I suppose it will. It's a good question. Yes, I suppose it will change whether you re-encode the logical 0 and you split it up, or the logical plus, but I would have to get back to you.
Thanks.
Yes?
You could easily detect X error.
Correct. Yes. Let me just explain what Ganpathy said. In the original code, we had 0, 0, alpha 0, 0 plus beta 1, 1. If you have a Z error on this code, this will give you a minus here, and this is part of the code space. So you will not be able to detect. It's very easy to see here that the distance is 1. But this kind of framework where you go to the dual basis is more general. It will serve us when we go to more complicated codes. One final question, and then we move on.
Yeah, when you return that phase flip, for that code space, you return plus L or minus L. So that only can correct the Z error, or that code space can correct the bit flip also?
This code?
Yeah.
This code can only correct phase flips. It's exactly the parallel. It's the same code. It has the same properties, but it just is written in pluses and minuses. So it's no different. It will not be able to correct bit flips. Bit flips will look like a change in phase in this basis.
So here, what you have written that 0L and 1N, this can correct both that bit flip or Z.
This can detect both bit flips and phase flips. This is why I ask you to show. It's very easy to see in the bit flip case. I want you to go to the plus basis to also see it in the phase flip case. Okay, let's do a small exercise. Let's apply Z. Let's apply ZI. Say to logical 0. Now what it will do, it will switch this into this. Now you have an orthogonal, you have a new state that is orthogonal to this one and to the original 0. So it's in a new error space. Okay, good. Let's talk.
Like, I think it's basis dependent only if like dx and dz are different. Like if they are both 2, for example, dx and dz, then the distance wouldn't depend on the choice of local basis for each of the qubits, because
Right.
If that was true, then error correction would be meaningless. I mean,
That sounds about right. Okay. So now we start with lecture 2. And we'll talk about we'll start with talking about stabilizers. Suppose we start with our large redundant space, Hilbert space, with n physical qubits. So the dimension of the Hilbert space is 2 to the power n. And now let's take a Pauli operator. We call it S1. And if you remember, Pauli operators have 2 eigenvalues. They all have either +1 or -1 eigenvalues. So we can partition this Hilbert space into the -1 and +1 eigenstates of S1. Take S1, it's a member of the Pauli group, of the n-qubit Pauli group. I'll remind you, I insist, no i's. We can do this kind of thing. It's an arbitrary tensor product of i's and x and y's and z's. The number of eigenstates that have eigenvalue +1 equals the number of eigenstates that have eigenvalue -1. Try to convince yourself of that. Hint, the trace of any Pauli operator is 0. And so the dimension is cut in half. Now let's do this again. Let's take an operator S2, such that S2 commutes with S1. S2 is again a Pauli operator. What will happen now? I will partition this state in 2 once again. I assume, of course, that they're different. Right? So now I have the +1 +1 eigenspace, +1 +1 -1, -1 -1, and -1 +1. And I can do this on and on and on. In the end, I'll get a nice pizza with many different slices. And each slice corresponds to a different configuration of pluses and minuses. In particular, we'll focus, for the sake of convention, it doesn't really matter, on the simultaneous +1 eigenstates of all of these operators. So we have S1 up to SR. And all these operators commute with each other. We'll come to the condensed matter and analogs. I have nicely compartmentalized those in one page. All these S's commute with each other. Why do they have to commute with each other? Otherwise, they wouldn't create, you wouldn't be able to measure them or to assign a simultaneous set of eigenstates for all these operators. So maybe you see where this is going. We'll start with some nomenclature, some definitions, which are, in the end, we have to go to some jargon, nothing we can do about it. The set of S's we call the generating set, or a set of generators. We'll see in a minute what they generate. They're also called check operators because we're going to check them, check their eigenvalues. And as we said, they all have to be mutually commuting. In particular, minus identity can never be chosen here because minus identity commutes with no other Pauli. Now we define the stabilizer group, which is simply the group generated by these R polys. So any multiplication of S's here still commutes with every other multiplication of S's. They form a group. We call this big S. And these brackets denote that this is the generating set of the group. In particular, we can write every element in S as the first generator to the power of 1 or 0 times the second generator to the power of 1 or 0, etc. Because multiplying S's together just gives you the identity. So you can it only makes sense to take the power of 0 or 1. This is the stabilizer group. And now, because it's, in some sense, it stabilizes a state, we'll get to that in a second. So we have now the code space, or what's called the stabilizer code. So now we define a code using these concepts. And the code is exactly this green slice of pizza all over there. Is it green? No, it's orange. Remember, a code is nothing else than a two-dimensional subspace or 2 to the k dimensional subspace of a 2 to the n Hilbert space. So the code space is the simultaneous +1 eigenspace of all stabilizers, or all the stabilizer generators. It doesn't matter. In other words, C is the set of states psi such that Si psi equals +1 psi for all generators. You could define a code where you have states spread all over. However, a stabilizer code is a family of codes where you can describe the code space as a simultaneous set of eigenstates. So it's not the most general code, but it's a very general code. So no, because this is not a geometric picture, or it's not some phase space that I've drawn. It's just an abstraction. When I divide it in two, it's not a nice partition in two, where you have some geometry. It's just a picture in the end. We'll see many examples. I'm sure I'll convince you. And sometimes you cannot write a code in such a way as a simultaneous +1 eigenspace of a set of polys, then it's not a stabilizer code.
If all this partition you made, all this partition of equal size.
Yes. This is a property of poly operators, which is why the poly group is so useful.
So then let's say we have k qubits. So then this space is like 2 to the power n divided by.
We'll get to the counting. We'll do some counting soon.
So I'm trying to get
Yes. Yes. We'll spend an hour talking just about this kind of stuff. So bear with me. Any questions? Well, before questions, there was a question here about dimensions. What is the dimension of C? Anyone has an idea? The dimension of the whole space is 2 to the n, and I have R stabilizers. And so the dimension of C is 2 to the power n minus R. Okay? Every time I have a stabilizer, I cut it into 1/2. And so K of the code is n minus R. I count the number of physical qubits. I count the number of check operators of stabilizer generators, and I get the number of logical qubits. Of course, the generators have to be chosen as an independent set. Yes, each state, I regret this choice of terms because I'm getting hungry, but each state in this slice is a part of the code space. And it has a dimension which in general is larger than 0 or 1. I'm not sure I get the question. There's many choices you can make. What I'm doing right now is I'm discussing a framework, a set of rules. And once the set of rules and the jargon are clear, we'll see how we use it to make smart choices about error correction. Yes. Thank you. I'm sure they will. Error syndrome. A syndrome is something you get when you do a diagnosis. Okay, when you check the measurement operators, you get the eigenvalue of a state, and it can be +1, -1. You get a string, a binary string, and this is the syndrome. So it's a binary string that you get of eigenvalues obtained from measuring the check operators. It's what we're going to do when we do error correction. We're going to measure the error syndrome. Good. I think this summarizes the jargon, and now we'll get to some examples. It won't surprise you. Oh, I've just erased it. It won't surprise you that we're going to go back to the 4-qubit code. I could specify a code by specifying logical 0 and logical 1. We're going to drop this. This is not sustainable. If I have 1,000 qubits, I'm not going to write a superposition of 2 to the power of 1,000 states. Rather, I'm going to describe them by the set of generators. So what are the generators of this code here? It's a question. So I'll take answers mostly from the back. Can you think of operators, Pauli operators, which when applied to 0 and 1, give you +1? Z, that's correct. I'm going to write it on the side. You'll see why. But it is a stabilizer. So Z, it always gives you -1 twice, and so it's a +1 eigenstate. XXXX, exactly. XXXX just means flipping this one with this one, so it doesn't change it. And it also flips the positions of, it flips these ones into zeros and these zeros into ones. You get back the same state always. This one I am going to write down. But you get the trick. ZZII is also a generator. Excuse me, not this one. ZZII. And so is IIZZ. These are commuting operators. They might collide, but they always collide in pairs of X and Z's. Note that ZZZZ I don't have to write it in this generating set because it's the multiplication of these two generators. Okay, the identity is of course a trivial stabilizer, and I have many more. I have 2 to the power r stabilizers, but I only need to write down the generating set. Good. So I have 3 generators. And so what's the number of logical qubits? N equals 4, R equals 3, K equals N minus R, so K is 1. 1 logical qubit is encoded here. By the way, let's do a poll. This generator here, does it detect bit flips or phase flips? Who says, everyone has to vote. Who says bit flips? Who says phase flips? No, this doesn't work like this. Okay. So the question is, suppose I apply this operator on a state. It will give me a +1 eigenstate if I'm in the code space, but it's going to give me a -1 eigenvalue if I'm out of the code space. Okay. So imagine I have 2 types of errors. I have XIII and I have ZIII. When is this operator going to yell? Let's try the poll again. Is this operator going to give a -1 eigenvalue for bit flips? Who says bit flips? Okay, who says phase flips? Good, much better. So you're right. When you have a phase flip, what happens? When you have a phase flip, on qubit number, this qubit here, you get a minus sign here, and you get a minus sign here. If I apply ZZ, well, the change is unchanged. It still gives me +1. But X, remember, it means flipping this state with this state. And then I get a -1. Okay? So if I apply X to this one, I get, I'm making a bit of a mess here, but I get 1, 1, 1, 1 minus 0, 0, 0, 0, which is -1 times the original state. Okay? So my X operators, my X generators typically detect phase flip errors, and my Z generators are going to detect bit flip errors. Let's do another small exercise. So I'm going to give you a state, and you're going to have to tell me what the syndrome is of that state. What is the syndrome of 0, 0, 0, 0? Excuse me, the 1 here. -1, 1, 1, 0. It's a legitimate state, and now I'm measuring the check operators, and I'm getting syndromes, I'm getting eigenvalues. So what is XXXX going to give me? -1. If I flip these states, I'm going to get -1 times the original state. How about ZZII, the first generator? +1, okay? These 2 qubits are the same. ZZ measures the parity of these 2 qubits. So I'm going to get +1. How about IIZZ? IIZZ is going to give you -1 because, well, the parity here is odd. So I'm going to get 1 minus out, not 2. So this is the syndrome of that state. I have diagnosed my errors. How about 0, 0, 0, 0? Let's start from the other side. If I apply IIZZ, what do I get? +1. I have the parity here is even. What about ZZII? Also +1. What about XXXX? Raise your hand if you have an idea. It goes to somewhere else. So what will the result? I measure an operator. It has to give me a result. 0? And the eigenvalues are always either +1 or -1. So I get a random outcome. I am not in the code space here. I'm not even in one error space. I'm in a superposition of two error spaces, and I have to collapse myself to either +1 or -1. So if I get +1, where have I collapsed myself to? Note that I can write this as 0, 0, 0, 0 plus 1, 1, 1, 1 plus 0, 0, 0, forget the factors of 2, minus 1, 1, 1, 1. Okay? Now this is an eigenstate of XXXX, and so is this. This would give me, well, is this a +1 eigenstate? Yes, it is. This is the -1 eigenstate. So if I get +1, I collapse myself onto the code space. If I get -1, I collapse myself into this particular error space. Okay. In other words, I wasn't in any slice of the pizza, but by measuring the check operators, I can find myself to either one of those. More questions. What are the stabilizers of this state? This is a Bell state. First of all, how many stabilizers are there for this state? 2. Why? I have 2 physical qubits. I have 0 logical qubits. I just have a state. And so I need 2 generators to specify a state. What are my generators? ZZ and XX. Okay. And finally, what is the stabilizers? What state is stabilized by X and Z? Zero plus 1. So if I apply Z to 0 plus 1, what do I get? 0 minus 1. No, so 0 plus 1 is not an eigenstate. It was a trick question. Very nice. These two don't commute. Okay, so they don't have a state that is specified by these two. And so C is the empty set, if you like. Good. I think you got a bit of the idea now. And as I said, here you maybe don't see the huge value of this, but when we get to larger and larger codes, it's going to be very convenient to start writing the codes in this representation. It's much more compact. Can you repeat? Maybe with a microphone.
The choice of stabilizer group generator is unique in this, or it can be any.
The question was, is the choice of generators unique? The answer is no. As someone said, I could have chosen here Z, 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 Z. As long as they are independent and they generate a stabilizer group, it's fine. Very often we'll want to choose a particular generating set. For example, maybe you can create a generating set that is local, that acts on neighboring qubits. That would be nice. Maybe you'll get the topological code. Okay, but in principle, you can have a very large number of equivalent generating sets. More questions?
It seems you require like the first to write down all the states, and then you have to find out the set of all commuting some commuting operator that have simultaneous eigenstates of this. So is there any way we can generate this code space itself by some generator?
Is there a general way to start with a code specified in the as a wave function and then go to a generating set? For sure, for specific codes or families of codes, there is a very efficient way of doing this transformation. I do not know if it's in general an easy thing. I would have to think about it. So I don't know, I cannot give you a general statement. Luckily, we don't have to because we're going to ditch this representation completely. More questions or a final question before we move on? Good. Now we're going to see how we can formalize the idea of error correction with stabilizer codes. Suppose an error happens, and again, I will be concerned with Pauli errors, but it doesn't matter. It's just we want to keep this nice structure. So what happens when we apply an error or some Pauli operator E, which is an element of the Pauli group? And let's start thinking about the options. The first option is that E is a stabilizer. That could be. So E is an element of the generating set. In other words, E psi equals psi for all psis in the code space. In other words, E acts trivially on the code space. And so E is not an error. Whenever I act with the stabilizer, I don't have an error. In the sense that I don't map to wrong states. Okay, this is an easy one. What if E is not a stabilizer, but instead it anti-commutes with one of the stabilizers, or more, but at least one? So number two, E is not a stabilizer. And it anti-commutes with at least one stabilizer. Let's call this stabilizer Sj. What can we say? Suppose I have this error applied to my state. Now I want to check the eigenvalue of this state. So what can I do? They anti-commute. So I can push the S inside. What is Sj on psi? It's psi. So Sj is an Sj is a stabilizer, and so it's a plus one eigenstate. So I get minus E psi. So if I measure Sj on E psi, what do I get? I get minus one. Okay? So E psi is an eigenstate of the stabilizer. Still is. It's still in my pizza. My pizza is no longer there. Still in my pizza, it just moved to a minus one slice. So E times psi is not in my code space anymore. It's not in a simultaneous plus one eigenstate, and so it's detectable. I have measured a non-trivial syndrome, and I have detected an error. So an error is detectable when it has when it anti-commutes with at least one stabilizer. Is this it? Did I saturate all possibilities? Excuse me? This we cannot have. Pauli is always either commute or anti-commute. What else could happen? Exactly. We could have a Pauli that commutes with all the stabilizers, but it's not in the group. Can you think of an operator here that does this? Good. XXII. You can try as hard as you want. It commutes with all of these, but you can never multiply the generators generators and get that one back. So third option, E is not a stabilizer, but it commutes with all stabilizers. And so what's the syndrome going to be? What's the syndrome of such an operator? It's plus ones, it's all plus ones. Right? If I do this trick, the same thing now, this equals E on Sj psi, which equals E psi. And so it's a plus one eigenstate. Good. So now we have a problem. Exactly. I'm going to bring back pizza. I started in the plus one eigenspace. In the first case, case number one, I stayed inside the code space, but I acted trivially. I didn't do anything. It was a stabilizer. In the second case, I moved to an error space. In the third case, I stayed in the code space. I'm in the set of plus one eigenstates, but it's not a stabilizer. And so it doesn't act trivially on psi. Remember, E psi is not equal to psi. Otherwise, it would have been a stabilizer, right? And so it does a non-trivial operation on this slice. What would I call this kind of error? It's a non-detectable error. What else could I call it? It's a logical operator. If I want to do a computation on my code, I need to apply this kind of operator that leaves me inside my code space, but it shifts things around. So it's both things I want to do and both things I want the environment definitely not to do. So it's an undetectable error. And it's a logical operator. Let's check. Someone said that this is it's not a stabilizer, but it commutes with all stabilizers. What does it do to the logical zero? It takes you to the logical one. So it's a logical X operator. It moves you from logical zero to logical one. And now we get a nice picture. First of all, we can define a new concept, which is the distance. But before that, what do we call this kind of operator mathematically? We say that E is an element of the normalizer of S. Normalizer of S in this case means that it commutes with all stabilizers, but it's not a stabilizer. This is the way we write it. Sometimes this is written slash. Good. And now we can define the distance of a code. The distance of a code, of a quantum code, is very similar to the distance of a classical code. In a classical code, it was the smallest number of bit flips that I needed to apply to go from one code word to another code word that's not the same. Here, the distance is the smallest operator that is in the normalizer of S minus S. So this is a logical operator. That's non-trivial. I want the smallest one. What do I mean by the smallest one? The one with the smallest number of non-identity. Okay, so it's called the weight. The weight of IIXZ is 2. Okay. Now I have a new concept, which is the distance of a quantum code. S is a set of stabilizers, which is generated by the generating set. And when I say NS minus S, I mean it commutes with all stabilizers, but it's not itself a stabilizer. The second nice thing is now we can, and this was a question you had before, Yuval, is we can write down a general criterion for error correction. Let's start with error detection. Error detection criterion. And these are called the Kneel-Flam conditions. Kneel-Flam did it for general codes, not for stabilizer codes. Error detection conditions. And it might surprise you how simple it is. EJ, I have a set of cross operators of errors. I want to know if it's a detectable set. Can I detect those errors? All I have to do is to check that for all j, EJ is not in NS minus S. If it's a stabilizer, I cannot detect it, but I don't care. If it anti-commutes, I can detect it. It goes to another state, another subspace. It's only when it's a non-trivial operator that I'm in trouble. Yes, it's maybe non-standard. I just always, there's a quotient group, and then there is, this kind of thing, and I always mistake between the two. So I'm just going to write minus S. It's a normalizer. It means in this context, or the centralizer, if you're familiar with that. It means all the operators that commutes with S. It's more than S. We know that there are more operators that commute with all S's. Yes. So NS is the set of all stabilizers plus all logical operators. It's all operators that give you +1 eigenvalues. Okay. More questions? Questions about this? Yes. It's the minimum over all logical operators. Minimum weight of any logical operator. We saw this operator, right? But what about y, z, z? This is also a logical operator. It is not a stabilizer. It has weight 4. Okay, but the distance is not 4. I want to go to the smallest logical operator. How did I get this? I multiplied this by this stabilizer. A multiplication of a stabilizer with a logical operator is the same logical operator.
One question.
Yes.
Can you clarify what mod of E is, the notation? I didn't get that.
What is this?
Yeah,
Okay.
no, the mod of E. I mean, the absolute value.
What is the absolute value?
Yeah.
This is the weight. So it's the weight of E equals the number of non-identity operators in E. Okay, I gave this example. If my E is I times X times Z, the weight is 2.
Another naive question. So, I mean,
Why is this the distance? It's the smallest number of operators that the environment has to apply to ruin my logical state.
no, one more naive question. So this, what stops me from defining a larger S with E included in it? I mean, so I could define a
Very
set.
good. Good.
So in particular, that would be a smaller code space or
Yeah,
something.
I got the question. Let's see. So to answer this question, let's find another operator that is in NS. For example, the logical Z operator. What would that be? Hint, it's comprised of Z's. Yes, good. Z, Z, I. Again, commutes with all of these. What's the problem here? Well, not a problem, but what could I say about these two? What's the relation between these two? They anti-commute. Okay, so elements of the normalizer of S, they all commute with the stabilizer set, but they don't necessarily commute with one another. I can't just put them in my stabilizer set. There is a generalization of stabilizer code called subsystem codes, which allow non-commuting observables. We're not getting into that. But in general, note that these, because they're Pauli operators, right? They're logical Paulis, they must anti-commute. Otherwise, they wouldn't define a logical qubit. Okay. We talked about the error detection conditions, but what about the error correction conditions? If I want to correct errors, I must detect them, but then I have to bring them back to the code space. In particular, what cannot happen is that I apply an error, but I thought it was another error. Remember, in the case of the 4 qubits, I had two operators, two errors that gave me the same syndrome, that brought me to the same space. If I apply the wrong correction, I should never get a logical operator, because then I change the state without knowing it. So the error correction conditions and this is the, these are the Nil-Laflamme conditions. It just says that EJ or EI times EJ, or rather for all I and J, we want EI, EJ to not be in NS minus S. That's all. I have some set of errors, EI, and I want to know if they're an error detectable set. An error correctable set. All I have to do is to take pairs and check whether when I have EJ and I correct it with EI, I have to make sure I don't apply a logical operator. Okay. It's okay if these two don't commute with the stabilizers, because then that means that these errors are in orthogonal subspaces. It's okay if they're in the same subspace. But then if I apply one to the other, I don't want a logical operator. Maybe this is time for one example. Let's write a bit of a different notation, which is very often used. There's the set of stabilizers, which is just these generator operators written down in a matrix form. It's nice to get used to. Every row is a stabilizer generator. Okay, so this is my code. It's my 4-qubit code. It's always the same one. And now I ask, well, I have a set of errors. I, Z, I, Z, Z. My quantum computer doesn't have any bit flips. It's, it's my Majorana qubits or something like this. I don't know. I only have phase flips. Oops. I, Z, I. And I want to know, is this a correctable set of errors for the code defined by this parity matrix, by this syndrome matrix? Okay. Now I have to start looking at pairs of operators. If I look at this times this, is it okay? So I times ZII gives me ZII. Is it a problem? Is it okay, this one, or not? Does this belong to NS minus S, this operator? No, it does not belong to NS minus S. Why? It anti-commutes with a stabilizer. Which one? The first one. It anti-commutes with the first one. The first one is going to yell at you. Okay, we're good. What it means is that this one and this one have different syndromes. You can set them apart. Same with these two. But what about these two? If I multiply these two, I get zi, zi. What about this? It commutes with all check operators, but it's not the check operator, right? This is the one, it's this guy. So this set is not detectable and not, sorry, it's detectable, but it's not correctable. Now I switch to a better quantum computer and I have these kind of errors. What about this pair now? What if I multiply this E by this E? What do I get? I don't hear you. I get a stabilizer. I get this stabilizer. In this case, we're good. If I mistake, they have the same syndrome. They both give me a -1 on the same syndrome because they commute, sorry, they anti-commute with this one. But if I make the wrong decision and I apply this one after this one has been applied, I have a stabilizer. So I go back to my code space with a trivial operation. Good. So this is error correctable. If they have the same error syndrome, that's okay. This means that their multiplication is in NS. Okay, because if they have the same syndrome, if you multiply them, they have, the -1s cancel each other out. So you get +1 eigenvalues. So it means that the multiplication has +1 eigenvalues. But then you have to make sure that it's a stabilizer. Does that answer your question? No. Oh, if they have different syndromes, you're good. This holds. You're not in NS. So it's okay. If you anti-commute with a stabilizer, this applies.
Sorry, a quick question. I'm a bit confused about the status of this I.
Yes.
You call it an error, but it's the identity operation, right? And wouldn't one naturally include this I in the stabilizer group as a neutral element or something like that?
Okay, good. So I is a Pauli operator. That's one thing. It's always a stabilizer. It stabilizes every state. I can see it by just squaring xxxx. I get I. And yet itself, it's trivially, if I multiply this by itself, it's trivially a stabilizer. But I have to check that it's multiplied with other ones, that it's okay. You can notice that EI times EJ, if EI is identity, then together they give you the error detection conditions. This goes back to just one operator. So this condition basically tells you that every error needs to bring you to an error space. Okay, I think I missed.
Confused.
Yes. It's not an error, strictly speaking, but it has to be included in your error set. So the identity is a thing that can happen. Remember when we talked about cross operators, very often the identity is a cross operator.
But it's also an element of the stabilizer group, right?
Yes. Yes. Oh, I have more errors in here, by the way. All the stabilizers I can put in here. XXXX will be fine. This was a non-exhaustive list. Good. Oh, a generator for the error space. I would have to think about this. I think no. I think no. They don't form a group. In particular, I can have two errors that are correctable each, but when I multiply them, they might not be correctable. I'd have to think about this. Okay. Is it true? Yeah. Yes, yes. So I, ZI, and ZI, II are all correctable, but their multiplication is not correct. Good. I want to talk very briefly, this is kind of a last minute decision, about CSS codes. They are an extremely important subset of the stabilizer code family. Again, almost all codes I know of are stabilizer codes or cousin. And almost all codes I know are CSS codes. And I think the reason is that very often you can map a non-CSS code to a CSS code. Okay, so you get extra structure for free in some sense. CSS stands for Kelderbank, Steen. Sure, of course. Maybe he got a phone call now. I don't know. There's a Nobel Prize in physics. Just, I think these like one of these minutes. Just for those of you who don't know what I'm talking about. Okay. The CSS code is a method. Well, the CSS framework is a method of taking two classical codes and merging them into a quantum code. We want to rely on decades of research in classical error correction. We want to use those insights to create quantum codes. In fact, some of the most modern quantum codes have been created by, for example, Irit Dinour is a colleague of ours at Weizmann. She's a classical computer scientist, and yet she can take two classical codes and combine them, and voila, she has a quantum code. It's a very useful framework. All the codes we've discussed so far are CSS codes. Essentially, in one sense, a CSS code is any code in which the parity matrix can be divided into X checks and Z checks. Not always you can do that. Sometimes you have a stabilizer that is XXZZ. You can't get rid of it. But if you can get rid of these Z's, and you can write all stabilizers either in one form or the other, then it's a CSS code. So I've told you how to recognize CSS codes, but let's go in the other direction. The other direction is I take two classical codes. Let's call them C1 and C2, or rather CX and CZ. It's a framework. It gives you more structure. And it allows you to take two classical codes, which can have certain properties, error correction properties. When you combine them into a quantum code, they will inherit some of these properties. Okay, so it's a technique. It has other advantages. In this whole lecture series, we're not going to talk about computation, only about storage of quantum information. But just for the experts, CSS codes can do certain types of gates in a fault-tolerant way, transversely. So they have all kinds of advantages. So how do I define a classical code? Well, I could tell you which strings are the code words, but again, I can just give you a parity matrix, right? So this is a parity matrix of a classical code. What does it mean? It means that every code word has to satisfy HC equals 0. The code word has to be in the kernel of H. So what code words are in my code if this is my parity matrix? What does this tell you about the code words, about C? One to 0. So it means that if I have a string of 4 characters, it means that x1 plus x2 plus x3 plus x4 has to be 0. In other words, that's one option. Another option. 0, 0, 0, 0 is always a code word of any parity. It has to be even, an even number of ones. As soon as I have an even number of ones, Remember, this is mods 2, yes? Okay, so if I have a code that's 1111, it means I need an even number of ones in my. If I have a bit flip, I can detect it because now I have an odd number of ones. This is classical code number 1. And now I have classical code number 2. It's 11000011. Now I have, this one checks whether the first two are the same and the second two are the same. And now you can see it coming, right? When I want to make a CSS code, I combine these two by turning these into X's and these into Z's. No, and the zeros into I's. Okay? And this will be a quantum code. But I need to satisfy, in order for me to do this, and here's where the structure comes in, I need hx times hzt to be equal to 0. I have a very strict condition on my parity matrices. Why? Who can guess? Again, 0 mod 2. What? Yes. What condition do I need to meet in order for these things to be legitimate? I need them to commute. All x's commute with all x's. That's not a problem. All z's commute with all z's. But I need to make sure that the x's and z's always come together in pairs. They always have to collide in pairs. Then they commute. This is what this condition says. So I cannot take any two classical codes and combine them into a quantum code. They need to meet, they need to collide in pairs, okay? So this one is okay because it collides with this in pairs, and this one is also okay because it collides with this in pairs. So it will satisfy this condition. I want to go to topological codes, or to the surface code rather. But I want to leave a few more notes or points of why this is so important. For one, if I can separate the stabilizers into X and Z, my problem of error correction separates into detecting bit flips and detecting phase flips. Okay, I can have two machines. Each one is responsible for its own errors. I couldn't do that if I had mixtures of X and Z's. Yes. It's arbitrary. I can change it to the other way around. So sometimes I want more protection on the X side. Sometimes I want more protection on the Z side. Sometimes these two are the same code. Then it doesn't matter. Yes, but they need to complement each other. And now I want to leave you with some homework of something that appears over and over again, but we won't have time to talk about it in detail. So this classical code has a distance. The distance is 2 because I need to flip 2 bits to go from one even parity code to another parity code. This one also has a distance, okay? Now my question is, what is the distance of the quantum code? And the answer is, it can be much bigger than either of the distances of the codes. For example, in the surface code, which we're going to get to in a minute, the stabilizers are very local, they're small. The codes, the classical codes, have a very small distance. Yet when I put them together and I create the surface code, the distance, the amount of protection I get can be gigantic. This is important to understand why this happens. If you have a moment, half an hour, try to read, browse the internet, ask ChatGPT, I don't care, but try to understand why the distance can be much larger. It will give you insights that are worthwhile. How am I with time? Surface codes. That's it. Okay. So Tomorrow, we're going to talk about surface codes. Surface codes are stabilizer codes and they're CSS codes. So if you're going to do the homework, do it tonight.
Excellent. Thank you. The first talk that finished on time.
Oh, do I have a few more
Questions?
minutes? No.
President, we'll give you a chocolate. Questions?
So I didn't get that NS minus S. So is that NS also include all the S?
Yes.
So it cannot, right? Because
I have an S. These are my stabilizers. Now I ask, what is a set of all operators that commute with all stabilizers? It includes S, because all stabilizers commute with all stabilizers, but it can be larger. This is NS. NS minus S is this. Okay? It's all the operators that are in NS, they commute with everyone here, but they're not part of the set.
so one more question I didn't get, like why we're associating this stabilizer group that it should be a
Why was it associated?
operator which have eigenvalue plus one only, because if you are given a set of states, these two states, let's say, so it should be like the maximum number of operators that can simultaneously have these two as eigenstates, right? I mean, so it might, I mean, we can have some other operator that commutes with the stabilizer group. Let's say, then we can simultaneously diagonalize all those. Then they can't have eigenvalue plus
You can
one
do
on.
it, but first of all, you cannot put in the two poly operators because then it's not a commuting set anymore. You could put in just that one. It would be a different code. You can always make your code smaller and smaller. That's okay. It's a different code then, right? You can have more stabilizers. You can make this much bigger. That's fine. You'll have more checks, but the number of encoded qubits will be smaller. Remember, the number of encoded qubits is n minus the number of stabilizer generators. Now you have to think, do I want more logical qubits or do I want a better protection? It's a trade-off.
So then in some time, then all plus one, so having all plus one eigenvalue may not be optimal. We can have some other set.
Oh, this is arbitrary. I have to pick a slice. Which slice you pick, it doesn't matter. It just labels these plus ones and minus ones.
So what can be a good given or two,
Maybe, yes. Good. We can talk after.
Is there a notion of distance in your code space, in your pizza slice?
Yes. We defined it. It's no longer there. But again, it's the smallest member of NS minus S. This is the distance. Oh, it's right there. Oh, I should use blue more often.
Okay, so if there is it possible to take this pizza slice and divide it into small segments? In each segment, you will have several states, and each of these states will be a logical state, such that small spontaneous deviation within these segments will be clearly errors, and then you pay the price of a smaller number of logical states, but a higher protection within the pizza slice.
I'm going to choose my stabilizer set so that all naturally occurring errors, all low weight errors take you outside your slice. I'm going to construct and we're going to see examples of this, a few examples of how to choose your slice or your stabilizers such that all low weight operators take you outside. This is what we're going to achieve. In particular, one of the main goals of the field, which has been achieved, is to have a distance that is proportional to n. So if I have 1,000 qubits, I get a distance of 500. Okay? And then no low weight operator can move you inside your code space. Any other questions?
Okay, so if not, let's thank Serge.